Let me just wait for a few minutes so that others can join, and then we'll start our session. In the meantime, let me present my slides. Hi, Sachin. Hello. Hello. Hello, Sachin. Am I audible?
Yes, sir, audible.
Yeah. Okay, let's just wait for a few minutes, like 2 or 3 minutes, others to join, and then we can start the session.
Okay.
Okay, then let's just start. Okay, so welcome everyone. Welcome to the problem solving session for the NPTEL course named Basic Thermodynamics, Classical and Statistical Approaches. And the instructor of the course, as you all know, Professor Arnab Mukherjee of IIT Pune. And this is the week 6 assignment sections. So in the week 6, probably there is no other lectures as such. So it is kind of a review of all the past 5 week lecture sessions, and mainly in the last 5 lecture sessions, whatever is being whatever discussed will be reviewed shortly in this in this week's assignment sessions, and then and in the meantime, if you have any questions or some conceptual difficulties to understand, and I can happily take those questions. And as you all know, my name is Dibyendu. I'm a PMRF fellow of IIT Kanpur in the Department of Physics. And this is a link of my website. Probably you can get it from the previous assignment sessions. And this is the link of the YouTube channel where you can get all the assignment sessions, and it's also like in the description of the YouTube channel you can get the link of notes that we do in these assignment sessions. And if you like the content, or if you like the lecture sessions, you can leave a comment, or you can like it. Okay, so let's just review, means in that sense, let's just recapitulate whatever we have studied so far. So in the first week, we mainly focused on zeroth law of thermodynamics. And there we actually studied about extensive intensive properties, concept of temperature, and so on. And then actually we studied thermodynamic variables, ideal gas equation, and first law of thermodynamics. And as you all know, first law of thermodynamics is the conservation law of energy. And also, like, we actually learned different processes like isothermal, isobaric, adiabatic, so on. And we later studied about real gas equations, because as you all know, in real world there is nothing like ideal gas. All will be real gas, because it has the gas molecules have some finite volume, and it exerts some pressure to the wall. And we knew what are the consequences of the real gas equation, and also like virial coefficients and all those stuff. Then we actually shifted our focus to know about different expansion, like Joule expansion, Joule-Thomson expansion, same thing, different. And we knew about Joule-Thomson coefficient also, to know how this temperature changes according to the intrinsic system properties. Like for ideal gas equations, it doesn't talk about any temperature change while expansion, but in real gas equations there are some considerations to know that it actually the temperature increases or decreases depending upon from the Joule-Thomson coefficients. And later we studied about second law of thermodynamics. Okay. Later we talked about second law of thermodynamics. Concept of entropy. And so I can actually ask a quick questions. Sachin, are you there? Hello.
Yes. Yes, sir.
Yeah. So tell me, or like try to answer one thing. If first law of thermodynamics is a conservation law of energy, then second law of thermodynamics, is it any conservation? Does it actually valid for any conservation principle, or is there any concept quantity for second law of thermodynamics? What did you expect?
Sir, I cannot understand your questions.
So the question is, in the first law of thermodynamics, we know that it talks about the conservation of energy. Okay.
Yes, sir.
So is there any analogy to say that in second law of thermodynamics, is there any conservation principle? And if there is any conservation principle, what is the conserved quantity? Is it clear? The question is clear.
सर मुझे समझ में नहीं आ रहा है क्वेश्चन, आप क्या बोलना चाह रहे हैं?
मैं जो बोलना चाहता हूँ वो है कि फर्स्ट लॉ ऑफ थर्मोडायनामिक्स में हम लोग एनर्जी कंजर्वेशन के बारे में बोल रहा है, वो तो पता है
जी
ना आपको।
हाँ।
तो सेकेंड लॉ ऑफ थर्मोडायनामिक्स में कोई कंजर्वेशन प्रिंसिपल है उसमें?
जो उसका हमारा सेकेंड थर्मोडायनेमिक्स में जो सेकेंड लॉ है, आप उसके बारे में पूछना चाह रहे हैं?
हाँ हाँ हाँ, सेकेंड ऑफ थर्मोडायनामिक्स के बारे में एक गेस करो कुछ भी।
सेकेंड लॉ में तो हम अपने जो मतलब उसमें हम ये वो करते हैं कि जो एनर्जी को हम फोर्स मतलब जो कूल प्लेस है उससे हम जब
बोलो बोलो, कोई नहीं बोलो, यू आर गोइंग नाइसली।
कि जो हमारा कोल्ड स्पेस होता है, कोल्ड स्पेस से अगर हीट हमें किसी वार्म स्पेस में लेके जानी है तो बिना हम फोर्स अप्लाई किए हम एनर्जी का ट्रांसफर नहीं कर सकते।
एग्जैक्टली। सो कुछ वर्क बिना कुछ वर्क किए हम लोग एनर्जी को कोल्ड से हॉट रिजर्वायर में लेके नहीं जा सकते। So here actually the conserved quantity, if you know, the conserved quantity is entropy. So entropy means, if you know it, like if you want to attempt to know that in very deeply, then entropy is actually highly related to information. So there is a conservation of information. I asked you the question from a like if you are curious about knowing those things, I'm just trying to give you some perspective about second law of thermodynamics. Maybe it is difficult to know at this point of time, but I just want to let you know that there is also a conserved quantity, that is information, or like the entropy. Okay.
जी
Okay. Good. Okay. So there is also a conserved quantity like this concept of entropy. So the entropy or information will be conserved in the thing. Okay. And then we talked about different machines, rather engines, because there are different like fundamental difference between machines and engines. Okay. And we talked about Carnot engine, Stirling engine, and so on. So far, whatever have been taught is it is a part of thermodynamics. Okay. So up to week 5, all the lectures are for thermodynamics, and thermodynamics part is finished. From week 7 onwards, sir will talk about information theory, statistics or probability perspective, how the uncertainty comes from probability perspective and its consequences on thermodynamics. That sir will talk about. Okay. So far these things are complete. So today actually all the problem sets or all the problems will be actually amalgamation of all the concepts of these 5 lectures. and we'll talk about these things. And Sachin, just we will don't think like that I'm asking a question, okay? We will discuss, okay? So as much as you can participate in this conversation, that will actually increase your confidence, and it will actually help you to grasp the concept, okay? So there are, like, what do you expect? What is the difference between engine and machine? What do you expect? The thermal engine and machine, what do you expect? Have you any answer about defining engine? What does engine do? At first say that. What does engine do? So engine actually does, it actually extracts some heat from hot reservoir, and then it actually throws less amount of heat to the cold reservoir, and in between some amount of work has been achieved. That is engine's role. Now machine actually do the opposite thing. It actually draws some heat from the cold reservoir. By doing so, we have to do some work, and then we actually put much more amount of heat to the hot reservoir, like refrigerator. So refrigerator is a machine, not an engine, okay? It's a reverse of that, but it's a machine, okay? Is it clear, Sachin?
Yes, refrigerator is a machine. So
Yes,
but लेकिन sir इससे जो refrigerator is convert heat energy to mechanical one energy to second energy.
I didn't get you. What is की क्या बोले?
मतलब जैसे हमारा जिसका मैं जैसे हम डिफरेंस हम बताते हैं कि जो मशीन होती है, मशीन हमारी एक एनर्जी को दूसरी एनर्जी में हमारा चेंज करती है।
Exactly.
जो इंजन होता है वो हमारा हीट एनर्जी को मैकेनिकल एनर्जी में चेंज करता है।
पूरा नहीं कर सकते, पूरा नहीं कर सकते तो पूरा उल्टा हो गया ना. So machine is not engine, right?
जी हाँ।
Yeah, it's a reverse kind of a thing, but ideal in ideal condition, machine should be a reverse of a engine, but sometimes there is nothing like ideal condition in real world, okay? Whatever you have said, it's completely right that machine mechanical energy को machine mechanical energy देके कुछ heat के ऊपर काम करते, और engine actually heat से कुछ mechanical energy निकाल के लेके आते. That's completely correct. Okay?
जी।
Okay. 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 Just let's.
ये जो स्टेलिंग इंजन है, मैंने इसके बारे में पढ़ा नहीं है।
What?
अब
What?
बता सकते? स्टेलिंग इंजन, कार्नोट इंजन तो पढ़ा, लेकिन ये स्टेलिंग इंजन कौन सा?
Starling engine is actually taught in the lectures if you just follow the lectures, and in Starling engine also I have discussed the problems based on Starling engine in the next assignment sessions probably, so you can actually refer to those assignment sessions, okay? You probably you can have the access of to get this lecture or the assignment notes. You can get it, right?
Okay.
So do you know how to get it?
एक्चुअली जो मतलब मैंने अभी बीटेक का मेरा फर्स्ट ईयर है,
Okay.
तो मैंने यूपी बोर्ड से किया है, तो मुझे जो कोर्स सर वो पढ़ाते हैं ना, जो टीचर्स, मुझे वो क्लियर नहीं होता। बस टोटल इंग्लिश में वो करते हैं, तो इसलिए मैं सिर्फ
Okay.
वहां से टॉपिक देख लेता हूँ कि कौन सा टॉपिक सर पढ़ा रहे हैं, उसको फिर
Okay.
मैं यूट्यूब पे वैसे समझता हूँ।
Okay. 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 So we will try. So that's why you can attend this session, and you can ask your questions, and we can actually discuss about those things, and it can be clarified. And I can, in the meantime, I can talk in Hindi, and probably that will help you. But also, you can know those things pretty well. Okay. तो
जी।
हम लोग तो स्टार्लिंग इंजन के बारे में मैंने कुछ प्रॉब्लम सेट्स का आंसर किए हैं, तो you can refer to the last assignment session and you can take the help from that, and if you have any problem from those things, I can take the questions from you in the next session. Okay.
Okay, sir.
Okay, nice. Okay, so let's just start this thing. Okay, Sachin, tell me, from this question you probably, since you have studied about these things, so entropy, so this is from the first lecture, so extensive or intensive property. Entropy is an path function, extensive property or intensive property? Do you have any answer? Do you know these things?
सर नहीं, मुझे इसका आंसर क्लियर तो नहीं, लेकिन इतना क्लियर है कि पाथ वो पॉइंट फंक्शन होता है
Exactly.
एंट्रोपी।
वो पाथ फंक्शन नहीं होता है और स्टेट फंक्शन होता है. Actually, absolutely correct. You are completely right. Okay.
पर ये नहीं पता कि एक्सटेंसिव प्रॉपर्टी है या इंटेंसिव।
Okay.
वैसे जहाँ तक कि मुझे लगता है इंटेंसिव हो सकता है।
Exactly, intensive हो सकता है क्योंकि, so okay, let's just for you I can define first those things. So path function means depends on the path the process undergoes. Now entropy तो state function है, entropy depends only on the initial state and final state, right? So it is not a path function, so this is incorrect. Now what is extensive property and what is intensive property? Now extensive property means it does depend on the size of the system. Means if size increases, that particular variable or that particular function will also change. And intensive is where it doesn't depend on the size. मतलब साइज के ऊपर डिपेंड नहीं करते. जैसे कि एक टेम्परेचर तुम अगर कोई छोटा वेसल में बोल रहे हो और बड़ा वेसल में बोल रहे हो, टेम्परेचर तो टेम्परेचर ही है, उसमें दैट डजंट चेंज. डेंसिटी दैट इज ऑल्सो डजंट चेंज अबाउट फ्रॉम द साइज. सो टी, रो, दीज आर इंटेंसिव प्रॉपर्टी. नाउ अगर मैंने 1 मोल गैस लिया और 2 मोल गैस लिया, तो जो अगर मोल बढ़ रहा है मतलब साइज बढ़ रहा है सिस्टम का, तो एंट्रोपी बढ़ना चाहिए, राइट? डू यू एग्री टू दिस थिंग्स सचिन?
यस सर.
तो अगर साइज बढ़ रहा है मतलब ज्यादा मोल्स है उस सिस्टम में, तो एंट्रोपी बढ़ना चाहिए. सो दिस थिंग शुड बी, दिस एंट्रोपी शुड बी एक्सटेंसिव प्रॉपर्टी फ्रॉम दिस डेफिनेशन. ओके, दिस इज क्लियर. ओके, okay, this is clear, right? Okay. Okay. Now, here is some interesting thing is, for which of the following process delta U, which is change in internal energy, less than 0 means it decreases, Q means heat exchange less than 0 matlab heat loss, and work done is 0 means इंटरनल एनर्जी इज ऑल्सो डिक्रीजिंग, इंटरनल एनर्जी घट रहा है, हीट भी घट रहा है, वर्क डन 0 है. कौन सा सिस्टम के लिए हो पाएगा? द फर्स्ट ऑप्शन इज रिवर्सिबल आइसोथर्मल कंप्रेशन ऑफ आइडियल गैस. नाउ as you all know that for isothermal compression, first option isothermal means T constant, delta T 0 means change in internal energy 0. So this option तो नहीं हो पाएगा. And also like compression means there will be volume change, so there will be some work. Second option, reversible adiabatic expansion of an ideal gas. Now adiabatic expansion के लिए, for adiabatic expansion Q equal to 0, no heat exchange, so this is also not possible. Third option, reversible isochoric heating of an ideal gas. Now isochoric means delta V equal to 0, that makes W equal to 0, but heating, so heating means there will be some heat exchange, so Q not equal to 0, and Q will be, since it is heating, Q will be greater than 0. So this is also not possible. One option is left, what is combustion of benzene. Combustion of benzene, you will provide some heat and you will combust the benzene, so they will provide some heat to get get some changes in the system. So since you are providing some heat, so Q less than 0, and also like from the heat, if it is conducting to immersed water bath, then its temperature also decreases. So this option is correct. Option D means since temperature decreases, so delta U less than 0, so internal energy घट रहा है, and you are providing some heat, so means like some heat is, you are providing some heat, so there will be no heating, and so Q less than 0, so and also like since these are isothermal, these are equilibrium, so W equal to 0. Okay, so this is the thing. Option D is correct. Now this is quite important. Is it clear, Sachin? Okay, so do not worry that you have some language barrier, that's why you cannot learn. You can learn, because science is all about basic concepts. It is actually, जब मैं सोचता हूँ कि कोई लैंग्वेज के वजह से अगर कोई साइंस नहीं सीख सकते, उसमें कमियां हम लोग साइंस एडुकेटर्स का है कि हम लोग वी आर नॉट एबल टू कम्युनिकेट, और हम लोग वो चीज़ सही से कम्युनिकेट नहीं कर पाते. तो कोई दिक्कत नहीं, तुम सीख जाओगे, बट यू जस्ट नो अबाउट लाइक इंग्लिश सीखना भी ज़रूरी है, आई नो दैट. सो you know about, you learn those terms like the science terms, and then you just try to like study those things in some Hindi textbooks, and later you can find those things in English textbooks also, and you can actually map those things clearly. Okay, so this option 3 says, for an isolated system which has not reached equilibrium. So system is isolated means there is no heat exchange, and there is also no the internal energy changes will be totally no change in matter also, like no heat, no matter, that is isolated, right? So let me define you the systems first so that you can know these things. So isolated means no change in heat. Heat means, sorry, it will not be heat, it will be energy and mass. There is also one thing, it's called open. There is actually change in everything, mass and energy. And there is closed system. Closed system, no change in mass, but energy can be exchanged. Okay. Now, for an isolated system which has not reached equilibrium, so here equilibrium is not reached. So the question is, the driving force for a spontaneous change. Spontaneous change मतलब तुरंत अगर कुछ change हो रहा है, मतलब the change is occurring very very rapidly. If that change is happening spontaneously, then which of these options is correct? Increase in entropy, increase in internal energy, decrease in internal energy, both A and C. Now, one thing you should know, that when these things are not equilibrium, are not in equilibrium, we actually cannot talk about internal energy change for sure. Why is so? Because the system has not been settled into the environment. So the internal energy is also like changing and it's fluctuating very rapidly. So we cannot talk about that. But one thing we can talk about surely, that is increase in entropy. Because as you know, for a system which is far from equilibrium, it is irreversible. And in the irreversible system, change in entropy is always increases. That is the catch of this problem, that since it is out of equilibrium or it hasn't reached the equilibrium, there should be an increase in entropy. Okay, so this will be the thing. Because, like, what is the logic behind this? Logic is, it has not reached equilibrium, so this is irreversible. Okay, it's clear, right?
Right.
Okay. Okay, let me go to the next problem. Next problem says, for a isobaric process occurring at 300 Kelvin, change in entropy delta S system, means change in entropy for the system, is minus 200 joule per Kelvin, and change in enthalpy for the system delta H system is minus 100 kilojoule. Now the question is, calculate delta S universe for this process. Now this is quite some kind of a we have to do some algebraic kind of calculations, and we can get the expression for that. Now first, what is isobaric? Sachin, do you know what is isobaric process? Hello.
Yes, sir.
Do you know what is isobaric process?
Isobaric, it means pressure is constant.
Exactly. Pressure is constant, or like the force exerted on those external force is constant. Now let me go to these things. So P constant. Now T delta S universe is heat exchange, so it will be Q minus T delta S system, right? Okay. Now we don't know the system temperature, but we know the universe temperature, or like the surroundings, that is 300 Kelvin. Now okay, sorry, here since it is thermal equilibrium, Tu is Ts. Now this Q, heat exchange Q, will be minus delta H system, the enthalpy, delta H minus T delta S system. That is the formula. Okay. Now if you put those things, delta H system is minus 100 minus 300 into minus 200, but this is in kilojoule. Okay, so this is kilo, so K I will put it here like this, and if you do that, then minus 100 and this is, so plus I will keep 60, so this is 2 times 30, this is 60, and this there will be 1 2 3 means 10 to the power 3, that will be here kilojoule, so this will be 40 kilojoule, or yeah. Now delta S universe will be 40 divided by 300. Now this is kilojoule, this is kilojoule into Kelvin inverse. Now if you do that, if you do these calculations, it comes to there will be, let me do the calculations. It will be 0.1333 times 10 to the power 3 joule per Kelvin. I have just, for kilo I have put it 10 to the power 3, and if you do that thing, 0.3, and you just approximated to that thing, so option B will be correct. Okay, simple algebra here. Okay. Let me go to the next problem. This problem, if you attend the previous assignment sessions, these are actually, it will be pretty easier, since these things actually have been discussed in the previous assignment sessions. That Sachin, have you actually referred any assignment sessions of this course previously, or like this is the first time you are coming, or you are seeing the assignment sessions?
जी सर, मैंने पहले भी 1-2 सेशन किए हैं।
Okay, okay, okay. So I will recommend that you should first like you should see those things, and in the meantime, in this weekend, you can refer to those lectures or the assignment sessions. That will help you, okay, because there are several problems, and there are some the answer or like the detailed calculations are provided, so it will help you to understand the system, okay.
Okay.
Okay,
So 1 second, last question is preview.
what I didn't get you. What are you asking?
Can you show me last question, please?
Yeah,
Okay, sir, fine.
I'll give you all the this lecture notes or this assignment notes, because I have to actually today we have, because this is the revision of the previous lectures, so I have actually 19 or 20 number of questions, so I have to finish those things within 2 hours. So that's the thing. So that's why, and also like this shouldn't take much time, because concepts are actually discussed previously, okay. Now here the question is, some equation is given, like the this thing, this BaCO3 plus 2HCl, and some product is given. The question is, for the above reaction, what will be the value of delta U minus delta H? Okay, so Sachin, do you know how to do that, or?
No, sir.
Okay, so uh, now if you know the chemical reactions, like if you follow the chemical reactions lecture video, then you can know that this delta U minus delta H, that actually delta H actually is UF minus UI minus nRT. Some kind of N means here number of mole changes of like product, and the here this is the equation, so this will be a product, some product in the right hand side, the products, and in the left hand side the the reactants. So if the net, like uh, net product change is some finite moles, then it actually becomes the change of this delta U minus delta H is minus nRT. So n means like number of mole changes from products to the reactant. So these things is, so let me write, okay, products and reactants. Now here and it should be gaseous. So this is solid, this is aqueous, this is also aqueous. Aqueous means in water solution. And this is also liquid. So only 1 mole of CO2. So delta N then should be N product minus N reactants. That should be 1. So that should be minus RT. Okay. So option 5 or option E is correct answer. Okay. Okay. It's pretty simple problem. Okay. Next, go to this problem. This problem is easy. Sachin, you can do this, right? Hello.
Yes, sir.
This problem you can try. This is
जी
easy. So can you just try for few minutes, like 3-4 minutes?
जी सर.
No. Okay, and then we can discuss about this problem. Okay.
Here six answer.
So according to you, the answer is 6. Right? 6, right?
जी
But I disagree. Let's just do that. Okay. Okay. So question is, what is the work done ideal gas, that what will be work done in going from state 1 to state 2. Now this is defined as W is minus P del V. Okay. Now along this line, del V equals to 0. So in that thing, W equal to 0. Now along this line, P is fixed at 2. So P is 2. V initial is 5 and V final is 1. Okay. So V initial is 5, I don't know unit, and V final is 1. So W is minus P means 2 times Vf. So delta V is Vf minus Vi. So Vf is 1, Vf is minus 5. So if you calculate this thing, this will be 8. Right? Is it clear? So our right option should be 8 unit. Is it clear, Sachin?
Yes, sir.
Okay. So you probably did some algebraic mistake. It happens sometimes. So that's the.
सर इसी तरह से एक क्वेश्चन जो इसमें असाइनमेंट था उसमें आया था, तो वो मैंने इसी तरह से किया था कि जो मतलब उसमें पीवी और डायग्राम दे रखा था और उसमें एक साइक्लिक ट्रायंगल था, तो उसमें वर्क डन जो हमने निकाला था उस ट्रायंगल का जो एरिया था उसके इक्वल करके वो किया था फाइंड।
नहीं,
तो यहाँ पे भी मैंने सेम यही वो किया था।
that should be possible if actually that should be possible if that 2 and 1 will be connected. That will be a cyclic process. This is not a cyclic process, right?
जी,
Because this is that should be the case if that 2 actually then comes to 1. That will be a triangle, because here 1 to 2 there is no connecting lines, right?
Yeah, I understand.
Okay, so that's the thing. So that we have to do in this way. Then if you do that way in the cyclic process, that is completely true, that we have to know the area of the triangle, because that is the contour of the PV diagram or PV trajectory. From that you can actually get it. But here this is not a cyclic process. This is just from 1 to 2. So this is one way process. It doesn't go back to 1. Right? Okay, that's the thing. So this is 8 unit. Always remember to write the unit. Since here it is unitless, we will just keep like this. Now this question is very much pedantic. It's easy. For a chemical reaction in the gas phase at constant pressure and temperature, work has to done by the system when. Now that I actually give you the clue in the previous questions. So question is, the chemical reaction in the gas phase at constant pressure and temperature, work has to done by the system when number of moles of reactants products is same. Number of moles of reactants is greater than the number of moles of products. So here the number of moles is same, means delta n equal to 0. Here means delta n means number of moles reactant is, in our logic, delta n less than 0. Here is delta n greater than 0. So that should be the case, because we have done the previous problem, right? This is minus RT. So here work has to done by the system when number of moles of products is greater than number of moles of reactants. Okay, this is simple, just theory questions, or that's from the statement kind of a question. Let's go back to the problem number 8. Problem number 8 says, which of the following conditions are true about maximum work? So these are like from the basic fundamental principles, basic concepts. It will be just from the from the fundamentals of the thermodynamics. Now, maximum work means the options are the change in the system takes place in a finite number of steps. So, finite number of steps means you have to do it quicker, right? You have to do it quicker. But whereas this will be irreversible. Whereas in reversible process we know it will be slower infinitesimally, and so that it can be with the equilibrium with the surroundings at each step. So this statement is incorrect. Any change taking place is thermodynamically irreversible. So from that also these things. So in irreversible process we know that the work done or work obtained is not the maximum, because there will be some dissipation. Now option C says the pressure of the gas is infinitesimally less than the external pressure. That is also not true, because pressure doesn't depend, or like pressure is not that much important here, because it is also like some kind of extensive variable, variable which is external to the system. So we have to know, or we have to talk about from the basic intrinsic parameters. That is also not true. Like the system is in thermal mechanical equilibrium with the surroundings at every stage. That can be true, because since it is mechanical equilibrium means there is no heat loss, or there is no change in heating. So means from the first law of thermodynamics we know delta U is equal to Q plus W. Since it is mechanical equilibrium we can neglect it 0, so W equal to change in internal energy. So all the change in internal energy will be due to the W. So that should be the case. The system should be in equilibrium mechanically with the surroundings at each and every stage of process. Okay? Logics are clear?
Okay.
Okay. Okay. Now this you should say, Sachin, try it. You can do it. You can do it. Question says, for which of the following processes delta S means change in entropy is 0? Option A says endothermic process. Option B says exothermic process. Option C says reversible adiabatic processes. Option D says isothermal process. Sachin, what should be the answer?
No, sir.
You don't know it?
No.
Okay. Okay, no worry. I will discuss it. Okay. Now, endothermic and exothermic, it depends on the enthalpy. So how much heat is actually extracted or given to the system for these things. This is not a thing. Isothermal process is delta U equal to 0. Now, reversible and adiabatic process is, in adiabatic reversible process, heat exchange Q equal to 0, and we can write TDLS equal to Q for reversible thing. So adiabatic means this and reversible means this, because we can write then a path function in terms of intensive variable and state function, and then from here we can write delta S equal to 0. So option C is the correct answer. Okay. So always know this thing. Adiabatic process means there will be no heat exchange. When the adiabatic process happens reversibly, means we can write heat exchange or a path function like heat as some intensive variable and some state function which is entropy. Then from that equation we can write delta is equal to 0. Okay, clear, right?
Endothermic process, what is this?
So endothermic and exothermic, it actually when like some kind of enthalpy changes. So enthalpy means, like, let's say an example, some kind of bombing is done. Okay, so it will produce some heat, or some kind of you put some kind of chemical at your hand, then it actually feels colder. So this endothermic and exothermic like this. So probably, like, since I am from physics background, so this definition actually changes. Like, just from physics background, it says if heat produces, or if heat has been extracted from the process, then it is exothermic. Means it thermal, there should be some more heat. And in endothermic process means some cold kind of thing, or like enthalpy changes is negative. From physics background, I don't know about the chemistry, but from the physics background. So main thing is, the main crux of the story is delta H, the change in enthalpy, is not zero, is not equal to 0 for endothermic and exothermic, and it depends on the sign. Delta is less than 0 or greater than 0. Okay, is it clear?
Ji sir.
Okay. Okay. And now, can you answer this, Sachin? This is probably from your kinetic theory of gases in the class 12. This is the figure says that so this is the Boltzmann distribution. You have read about it in 12 or not? Wien's constant, Boltzmann distribution. Okay, no worry.
T2 is greater.
T2 is greater. Why? There should be some explanation, right? You are saying T2 is greater. Why is that? Let me help you by drawing this thing. This is the maxima for this graph. So this and here this is velocity. Let me write it clearly. So which one has more probable velocity? This, because this is a probability curve. So here it is maxima, means it is most probable velocity. So which one, for which one the most probable velocity is higher, T1 or T2?
The most probability T2.
नहीं देखो, प्रॉब्लम इज कौन से ग्राफ के लिए मोस्ट प्रोबेबल वेलोसिटी ज्यादा है, इस ग्राफ के लिए है और इस ग्राफ
T1.
T1. So T1, for T1 most probable velocity is higher. Now from your knowledge, if a system has higher temperature, it will be higher velocity, right?
Yes.
That's the crack. That's the thing. So from that thing, you can say that T1 is greater than T2. Okay.
जी
Okay. This will be the right thing. There are some. If you probably refer to my first or second lecture, you can get that most probable velocity expression from there. Okay. Okay. So we will take 5 minutes break because my throat is breaking. So I will join. We will resume our discussion after 5 minutes. In between, if you have any questions, you can write on the chat box. I will join after 5 minutes. Okay, I will be there. This will be there. I will just take those questions after 5 minutes. Okay. Okay, Sachin.
ओके
Okay.
वेरी
Hello. Hello. Okay, in the meantime, I will wait for a few questions and then we'll start our discussions. Okay. No chat. Now, this question says a system changes its state from 1 to state 2 through path A and returns from state 2 to state 1 through path B. Now, path C is also an alternate returning path from state 2 to state 1. What will be the effect of the change in enthalpy of the system if the system undergoes these different paths A, B and C? Now, this is quite interesting to know that here in that system, delta H, the enthalpy, actually doesn't depend on any path. It's actually path independent. So for all paths, it will be equal for this system. So delta H so it will be for all path it will be equal. Okay. Now for a gas obeying equation PV equal to RT, the value of Joule's coefficient is, now Joule coefficient, if you remember the previous class, the Joule coefficient is eta J is defined as del T del V at constant U, and this is can be written as 1 by Cv times del u del v at constant t. Now for gas which is P equal to RT, u is only function of T, because this is ideal gas, right? Ideal gas. So del u del v at constant T is 0 because there is no other variation. So this will be 0. Okay. Got it? So there will be no change of internal energy with respect to volume. Now question 13 says an inventor, a smart inventor, claims to have developed an engine that takes in 200 megajoule at a temperature 473 Kelvin and rejects 40 megajoule at a temperature 273 Kelvin while delivering 30 kilowatt hour of mechanical work. Check whether engine is feasible or not. Okay. Now let me just first this W, which is 30 kilowatt hour, let's just convert the unit. For kilo, this will be 10 to the power 3 kilowatt to watt. Then hour means 36 hours second. So this will be watt second. And if you like do this will be 108 times 10 to the power 6 joule, means 108 megajoule. Okay, this is the thing. So question says whether engine is feasible or not. Now to do that, we know that for efficiency is 1 minus T2 by T1 or 1 minus Tc, cold reservoir by temperature, by Th. It is actually 1 minus Qc by Qh. Now since efficiency cannot be greater than this of this energy, so TCTH is 1 minus TCTH cannot be greater than 1 minus QCKH, or we can write this QH, this coefficient cannot be less than TCTH. There should be always greater than this, because if it is less than this, then we can get more efficiency. Okay. Now so it cannot be less than this, cannot be. So TCTH this is 273 and 473. So TC is 273 and TH is 473. So TC by TH is 273 by 473. So, and QC by QH is 40 by 200, which is 1 by 5, and this is 273 by 473. So we can say that here TC by TH is greater than QC by QH. But we know that it shouldn't be that, because always TC by TH should be less than QC by QH. So since this is the thing, so it violates second law, and this kind of machine is not feasible. That should be the right option. Okay. Okay, Sachin.
Yes, sir.
Okay. The logic is understandable, right? Let me just repeat it once again. So the logic is efficiency is 1 minus T2 by T1. We can write like this for a Carnot engine, ideal engine, but it is actually 1 minus QC by QH, means heat extracted from it is like heat thrown to the cold reservoir divided by heat extracted from the hot reservoir. Now if QC by QH is greater than TC by TH, then only the efficiency for this expression will be greater than this, right? If it is smaller compared to this one, then this efficiency will be greater than this. That can be visible. But for our case, we can see that TC by TH is greater than QC by QH. That cannot be the case, right? So this is the ideal limit, and here we can see that this is maximum, this is greater than this, or TC by T is greater than this. Hence this expression 1 minus TC by TH is less than this. This cannot be true. From that we can say that it violates second law. Okay, let me go to the other problem. Problem 14. Problem 14 says a gas obeying the equation of state P of V minus NB by nRT subject to Joule-Thomson expansion. Will the temperature increase, decrease, or remain the same? Can you do it? I can give you the I can give you the expression. The expression is for mu Jt is del T del P at constant H. It can be written as also 1 by Cp divided by T dvdt at constant P minus P. Okay, and Cp is greater than 0. Only this expression we have to calculate. Can you do this, Sachin?
Sir.
T dvdt at constant P, this expression, can you calculate it? I can give you one hint. makes the equation of state and arrange it in such a way that it will be like some kind of one in one side will be V, and other side can be written in terms of nRT. Let me write it then. Then V minus NB will be nRT by P, and if you do this, then V equal to nRT by P plus NB. Try this, okay? Just give some minute and do the derivation. Are you able to do the differentiation?
Yes, sir.
Okay, great, great. So the differentiation will be that. So now if you do the differentiation here, then del V del T at constant P will be nR by P, and if you put T here, then it will be nR T by P. Now if you put it in this expression, then mu Jt will be 1 by Cp, and this is nRT by P minus V, and V is this one, so minus of this will be minus nRT by P minus Nb. So this will cancel out, so it will be minus Nb by Cp. This is positive, this is positive, this is positive. So mu Jt is negative. But what is mu jet? Mu jet negative means del T del P at constant H is negative. Now in expansion, so here we can say that mu Jt is less than 0. In expansion, dP is always less than 0 because pressure is decreasing. So since this is the ratio of del T del P, so to make it negative, dt should be greater than 0. So temperature should increase, right? Got my point?
सर प्लीज रिपीट यहाँ से जो आपने बताया ये नेगेटिव साइन यहाँ से रिपीट कर सकते हैं आप?
I cannot hear you. What are you saying?
सर जैसे हमने इसको इसका डिफरेंशिएशन कर लिया उसके बाद हमने इसको जो है आपने ये बताया कि एन नेगेटिव होगा वी नेगेटिव कि यहाँ से समझ में नहीं आया मुझे.
Acha. Okay, great. Okay. So we have substitute the expression, and this will cancel out, and there will be minus NB. Now this expression is minus NB by Cp. Now we know that Cp is a heat capacity at constant pressure. This is always positive. N is number of moles. It is also positive. B is like finite volume of the molecules. This is also positive. So N, B, Cp all positive. This is a minus. So this will be mu J will be negative then. So mu J, this is the Joule-Thomson coefficient, is negative. Now Joule-Thomson coefficient is like del T del P at constant H, at a constant enthalpy. Means the ratio of the change of temperature and pressure. Now in expansion we all know that pressure decreases, means dP negative. Now it is the ratio of two number, one number is negative and the ratio is negative, so one number should be positive, dt should be positive, right? Is it clear?
Right.
Yes. So that's since dt positive means change in temperature increases, so temperature increases. That's the logic behind this. Okay, it's clear, right, Ebu, now?
Yes, right. Clear.
Yeah. Okay. This is quite interesting, but the problem seems very difficult, but it's not very difficult. The problem says calculate the total change in entropy for the process shown below. So process starts from 1, then goes to 2, then 3, then 4, then 5, and again reaches to 1. Now without doing any calculation, can you say the answer? But it actually need not to do any calculation. It is just theory. Can you answer it, Sachin?
No, sir.
Okay. Okay, no worry. Okay. Now, since it starts from 1, then goes to 2, then goes to 3, again to 4, then to 5, then it comes back to 1. So it starts from 1, eventually comes back to 1. Now we know entropy is state function, right? Now it starts from process A and then comes back to A state. So since it is cyclic, so it goes back to the same thing. So change in SA minus SA is always 0, right? So this change will be always 0. And you can see from here also, like here entropy doesn't change, here entropy doesn't change because this is in this axis. Here it decreases, then increases, then it increases. Now from this thing, if you get the slope, then it will be like this one. For this thing, this will be this one. So this goes from this direction, and this is this thing. So this is total, this thing total, this and this one. So this length and this length is always similar to this length. And since this is this direction and this is that direction, so that will cancel out and it will be 0. Okay? Clear?
सर मुझे समझ में नहीं आया, आप एक बार और बता सकते हैं?
Okay. Now, this process starts from a process 1 से start हुआ था, then 2 में गया, then 3 में गया, then 4 5 होके फिर 1 में लौट के आया है. Now एंट्रोपी स्टेट फंक्शन है, मतलब कौन सा स्टेट से स्टार्ट करके कौन सा स्टेट में आता है उसका डिफरेंस के ऊपर डिपेंड करता है, सिंस इट इज रिवर्सिबल. सो सिंस ये 1 से स्टार्ट करके फिर 1 में लौट के आया है, सो द चेंज विल बी, the state doesn't change, it stays the same, and we know that it will be SA minus SB, मतलब फाइनल स्टेट माइनस इनिशियल स्टेट. सिंस दो स्टेट सेम ही है, so entropy change will be negative, entropy change will be 0, because सेम ही स्टेट है ना. एंट्रोपी स्टेट के ऊपर डिपेंड करता है कौन से स्टेट में है, राइट?
पॉइंट फंक्शन.
हाँ, पॉइंट फंक्शन और स्टेट फंक्शन. और अगर आप इससे देख सकते हो कि ये जो इसमें है चेंज हुआ है, ये टीएस डायग्राम है ना. इसमें कैसे चेंज हुआ है जो हम लोग एक्स वाई ज्योमेट्री में करते हैं, तो इस वेक्टर कैलकुलस में, तो एस के बराबर कैसे चेंज हुआ है इस वेक्टर का, ए प्रोजेक्शन लेना पड़ेगा. और इसमें कैसे चेंज हुआ है, ए प्रोजेक्शन लेना पड़ेगा ना. ए दो प्रोजेक्शन, ए और इसका लेंथ इसका सेम होगा क्योंकि पूरा एक वेक्टर ज्योमेट्री है ना. ए इस डायरेक्शन में हुआ है तो मतलब ए अगर कोई एक साइन होगा तो इस डायरेक्शन में साइन उल्टा होगा, तो दैट विल कैंसिल आउट, सो इट विल 0. सो दो प्रोसेस में ही हम लोग देख रहे हैं कि एंट्रोपी 0 हो रहा है, राइट? नाउ क्लियर?
यस, क्लियर.
यस, ग्रेट. Great. Okay. Now, this is another problem. This problem says, during the quasi-static expansion of a gas in adiabatic container, the pressure at any point is given by some equation. This is adiabatic equation. Now, calculate the work for change from Pi Vi to Pa Vf. You can do this, right? This one, I will just give you the expression. Delta W is P dB. Sorry, dW. So delta W will be dW initial to final. It can be written as initial to final. This is defined as PdV minus PdV always. This is minus PdV. You can always know that this is minus PD. So now write it as I2F K by V to the power minus gamma dV. Now do this calculation and let me know what is this.
Option number A.
Option number A, right? That's great. That's great. Perfect. Now let me do it for your friends also. So this will be, now just write this minus K by, so okay, so this will be K V by gamma, or can be written as K V to the power minus gamma plus 1 divided by gamma minus gamma plus 1 I to f, or we can write it as k v minus gamma plus 1 divided by gamma minus 1 I to f. So now k v gamma, if you take common, then it will be k v minus gamma, there will be v, 1 v. So this can be written as p. So this will be this is p f v f minus pi vi divided by gamma minus 1, or we can write it as minus pi vi minus pf vf by gamma minus 1. Perfect. Right. Okay. This thing, Sachin, very simple. A real gas obeying van der Waals equation will resemble an ideal gas if option A, both A and B are large, option B, both A and B are small, option C, A is small but B is large, option D, A is large but B is small. Sachin, tell me the answer.
One.
Option A.
Yes.
No, option A is not correct. Let me write it. Okay. So the real gas equation for 1 mole is P inert. Now if A and B is large, then we cannot write P plus A by V square is P. When can we write? We write, कब मैं लिख सकता हूँ? जब A very very small, then we can write, right? Then this contribution will go to 0, then it will come back to P. And if you write like D to V, then also like this, V is very very small, no volume for the molecules, it will convert to this thing. So this will be right. A and B both are small.
Oh,
Right?
yes, right.
Yes. 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 That's true. Okay. Now, this question needs, if you do the previous assignments or previous assignment sessions, this you can answer it very promptly. This question says two blocks of the same metal. Okay, same metal means same heat capacity, because heat capacity depends on the intrinsic properties, like what is the material that it is built of. Okay, so same metal with same size are kept at different temperature T1 and T2. Now these blocks of metal are brought together, okay, and allowed to come to the same temperature. The change in entropy can be expressed as, so we have to calculate the change in entropy. Now answer me, Sachin, what will be the final temperature, the mixed temperature after bringing them together? Same material, same everything, same size, what will be the final temperature? What will be that? Can you answer it?
Sir, again repeat please.
Yes. Yes, I can hear you.
Yes, sir.
You know this thing. Okay, let me tell you. Let's say this is CVTF. So two rods, this will be 2 CVTF, will be CVT1 plus CVT2. The change in heat will be like the previous change from this one to that one will be the same thing here. So if you cancel it out, then TF will be T1 plus T2 by 2, right? Same amount of water. One is at 10 degrees centigrade, one is 50 degrees centigrade. Then what will be the mixed temperature? That will be 10 plus 50 by 2 means 30. That is the concept here. Okay, great, right? Now we know the change in entropy del S will be delta S1 plus delta S2, and this will be Ti plus Tf Cp ln Cp dt by T, because heat change is Cp dt at dq, means dq is Cp dt and this is T ds. So ds will be Cp dt by T. After putting that, this is for process 1. For process 2 will be same thing, Ti to Tf Cp dt by T. Now do this integration, Sachin, for me, and tell me what will be the integration of this Cp dt by T. Sachin, this integration Cp dt by T, this will be log, right? Cp
Sir,
ln T. So this becomes Cp log Tf by Ti plus Cp log Tf by Ti. So this is for 1, this is for 2, this is for 1, this is for 2. We know that Tf is similar for everyone because this is in this thing. So this will be ln Tf square divided by Ti1 means T1, Ti2 means T2. Okay,
yes.
let me add one page here. Just a minute, I'm adding a page. So from here you know that Tf is T1 plus T2 by 2. Now if you substitute it, then delta S will be Cp ln Tf squared by T1 plus T2, T1 times T2. So after substituting this T1 plus T2 whole squared by 2, then this is 4 T1 T2. That is the answer. So the answer will be option number this one, option C. Okay.
Okay.
Okay. Now this question says, which of the following statement is not true? Temperature gives idea about average kinetic energy and not the individual particles' kinetic energy. This is true. Whenever we are talking about like that, this is like theory, so I will give some statement about it. Okay. Whenever temperature, it is about macroscopic picture. So it doesn't talk about the, it doesn't talk about single particle. Okay, so this is right. If we remove some particles of the higher kinetic energy for a system, Maxwell-Boltzmann distribution will shift to the left hand side. So we have seen this graph, right, Sachin? So if so, this graph shifts to left if temperature decreases. Temperature decreases means lesser kinetic energy. So this is also true, right? So if higher kinetic energy term removed, T decreases. So now third option will come later. We'll talk about fourth option because I know the answer. This is third option. At lower temperatures, the Maxwell-Boltzmann distribution will be sharper and narrower compared to a distribution at high temperature. That we have observed, right, in the previous problems, that this is for one and this is another one, and this, if it is T1, if it is T2, T1 greater than T2. So that is also true. Option C is the only option C is left only. So that says since ideal gas have no potential energy of interactions, all gas particles will have the same kinetic energy. This is patently wrong because we have said that this velocity has some distribution, right? So all the particles have not same velocity, that means not same kinetic energy. So not same kinetic energy. Okay, so this will be option C. Is it okay?
Okay, sir.
Okay, right? Okay. Okay, so let's just see probably one extra problems and we can finish this thing. Now this problem says system changes from A to B on a diagram. Okay, now ACB, this path, heat flows into the system, Q is 84.4 and W is 31.65. Now question says, now if it does work in 10.55 in this way, then what will be the thing? Now since this point and this point, these 2 points, we know delta U internal energy, which is UB minus UA. This is Q plus W. So we go in this way, that way, any other way, delta will be same. So since system does the work, so this will be negative. So delta U will be 84.4 minus 31.65. Now we don't know about the other heat. This is Q, and we know this one is 10.55. Okay, this will be system does work, so this will be minus 10. And if you do, yeah,
W हमने निगेटिव लिया है, ये किस लिए लिया है एक बार बताएं.
what I didn't get you. What are you trying to say?
Is negative.
I'm not able to hear you. Hello.
So why take W negative?
So in chemistry, they take, if system does work, they take W is negative. Okay,
Okay.
this is the sign convention. Okay, just sign convention. So in physics, if you do some work, that will be positive, but in chemistry, this is just different. Okay. Got it?
Good. Yes, sir.
Yes, sir. Okay. Now if you do that, then Q will be 84.4 minus 31.65 plus 10.55. This will be 84.4 minus this is 21.1. This will be 63 point. So this is the right option. Okay. Okay. Now here this is Joule-Thomson coefficient calculation is there. So since in the previous problem we have done one Joule-Thomson coefficient problem, I guess. Yes, this is Joule coefficient problem. Okay, now Joule-Thomson coefficient problem. So this mu jt is defined as minus 1 by Cp del H del P at constant T. Now Cp is given 110 J K inverse mole inverse, and del H del Pt is also given. So you will just put it here. This is minus 1 by 1 by 0, and there is a mega, mega is there, this thing. So this will be minus, also minus. So minus and minus cancel out. 3.2 into 10 to the power 3. This will be 10 to the power 6. 6 joule Kelvin mole inverse. Now since this is in kilo divided by, so this will be the so this is joule Pascal inverse mole inverse, Cp in the reverse, so this will be joule cancel out, so 1 by joule Kelvin inverse mole inverse. Joule cancel out, this Kelvin mole inverse cancel out, Pascal inverse, and so this will be 1 by 10, since there is million here also, so 1 by 10 times 3.29 into 103, then Kelvin millipascal. And if you do the calculations, let me do it pretty quickly. 3.1 into 103. So this is coming as 3.02. This is coming at 3.0806. So there is no option. So these options are incorrect. This will be the correct. Okay.
Okay.
Okay. Any problem? This is simple formula putting problem, right? That's why there is no concept here. Only the values are there, and probably they have they just did it and did some typographical error, and that's why this is coming like this. Last problem of this session today. This says calculate the change of entropy involved in heating gram atomic weight of silver at constant volume 0 degrees centigrade to 30 degrees centigrade. The value of Cv is given as this. So now, so far, can you do this? Can you do this problem?
Yes, sir.
So this will be similar to that thing. That let me do this thing. That delta S will be Ti to Tf Cv dt by T, right? Right, Sachin? Hello.
यस सर, पर यहाँ पे CV आएगा, CP.
CV आएगा इधर, क्योंकि इधर सिर्फ बोला है कि at constant volume, not pressure. That's why CV. Okay.
Okay.
Okay. Because if you see this thing, then Q will be delta U minus W, and Q is delta U minus W, and this is P del V. So this is 0 since constant pressure, and delta U is Cv dt, right? And Q, if you write it Q is equal to TdS, then ds becomes Cv dt by T. Okay, this process is, can you follow this process? And now if you do the integral, what will be the thing? Can you do this for me?
Yes.
And tell me the answer.
log T आ जाएगा यहाँ पे, ln T.
हाँ.
TF.
Okay, this will be ln T, but there will be some limit Ti to Tf. Now this will be Cv ln Tf by Ti. Now put it, what will be Tf? Tf? What will be Tf?
फाइनल प्रेशर को,
Final temperature, not pressure. So this will be, this is in this thing 30 degree centigrade, but this is in centigrade scale. We have to get it absolute scale. So this is 273 plus 300 and 273 plus 0. Then Cv ln 303 by 273, and it is given 5.85 times
सर
ln of.
फाइनल, जब हम फाइनल टेम्परेचर करेंगे
हाँ.
तो T1 T2 अपन करेंगे.
I'm not able to hear you. Can you speak clearly? Final pressure क्या final? Hello.
नहीं सर, राइट.
Okay. Got the point?
Yes.
Okay. Now if you calculate the ln of 303 by 273 and times this 5.85, this comes 0.609. So this comes 0.609, but the unit will be, there will be calorie degree mole tha, so this will be calorie Kelvin inverse, right? T is in the below, so there will be calorie inverse. So this will be the correct option. Okay. Okay, so that's it. That is today's session, and until we will meet again, and if you have any question, then you can ask me in the next class. next assignment session, and probably from next assignment session we'll talk about the probability and statistical description of thermodynamics, or this statistical mechanics course. So, and we'll meet then again. Let me just stop the video. So thanks for listening.